PMO 2022, day 2, problem number 5, 24th round. For having next videos, subscribe my YouTube channel, turn on the bell, like the videos, and if you wanted more explanation, you can send message through my WhatsApp number here. Okay, problem number 5, it says find all positive integers n for which there exists a set of exactly n distinct positive integers, none of which exceed n squared, whose reciprocals add up to 1. Okay, so if you check for n1, we consider small examples. 1 over 1 is okay, so 1 is okay. If you consider n2, you can see because 2 squared is 4, so our numbers must be less than or equal 4. So because you should use two fractions, you can't use 1 over 1 because 1 over 1 is 1. And if you add 1 over 1 to any of them, it would be greater than 1. Now you have these three numbers, 1 over 2. If you check any two fractions, the sum is not 1. 1 over 2 plus 1 over 3 is 5 over 6. 1 over 2 plus 1 over 4 is 3 over 4. 1 over 3 plus 1 over 4 is 7 over 12. So for n2 it is impossible. I want to prove for all n except 2 it is possible. For n3 I do something, and then I want to generalize this idea. I say 1 over 2 plus 1 over 2 is 1, but the problem says distinct, and also we want three fractions. So you change 1 over n equals 1 over n plus 1 plus 1 over n times n plus. If you consider common denominator, you can check that this equality is correct. And I use this key point. So I replace a over 2, n is 2 here, with 1 over 3 and 1 over 2 times 3, 1 over 6. So 1 over 2 plus 1 over 3 plus 1 over 6 is 1. You have three fractions and 6 is at most. 3 squared is correct, so 3 is correct. I want to generalize this idea. I say 1 over 2, 1 over 2. I replace 1 over 3, 1 over 2 with 1 over 3 and 1 over 6 by this key point, because I call it star. So by star, I can say again, I can replace 1 over 3 with 1 over 12, 1 over 4. So for n4, for n5, I do the same things. So if I want to say for n, I do what? 1 over 2 plus 1 over 6. 6 is 2 times 3. 1 over 12, 1 until 1 over n times n minus 1 plus 1 over n. But it is only bad for the case, for example, look, if I want to use for 1 over 4, for n equals 4, I used 1 over 2. Let me tell you, I select which of them for this. I select this one, this one, this one, and this one. If you add all these numbers, you can see, because this plus this is 1 over 3, this plus this is 1 over 2, this plus this is 1 over 2, plus 1 over 2 is 1. But the problem is only in some cases. I know all of them are less than or equal, strictly less than the next one. The only bad case is when n is k times k plus 1. For example, 2 times 3, n is 6. So at first I consider that n is not k times k plus 1. I want to at first say that these numbers, these fractions satisfy the problems, and only in this case I don't consider distinct, and then I will see for distinct what should I do. So at first I check some of them. 1 over 2, 1 over 2 times 3, 1 over 3 times 4, 1 over n times n minus 1, for example 6, 6 times 5, plus 1 over n, 1 over 6. And then if you add up all these numbers, it would be 1 over 2, 1 over 2 minus 1 over 3, and then by telescoping rule, I can reach 1 over 2 plus 1 over 2, which is 1. And also the maximum denominator is n times n minus 1, which is less than or equal n squared. So the only thing I should pay attention is when n equals k times k plus 1. So here are the fractions I wrote them again. So the bad case when n equals k times k plus 1. So for k1, it is 2. We've proved that for 2 is impossible. For k greater than or equal to, I want to say that it is okay. So case 1, if n squared, now I should consider only this case, that n equals k times k plus 1. If n squared is greater than or equal 120, I tell one proof. For other n, I will tell another proof. So n squared greater than or equal 120 is if and only if n greater than or equal 11. It is equivalent. So Let me tell you, I do what? For n, I want to write for n. I write until n minus 2, and although I know all these fractions are different, and then I change 1 over 20 to 1 over 40, 1 over 60, 1 over 120, and you can check that they are not equal to any other fraction. I change one of them to 3 other fractions. So n minus 2 fractions I had, now I have n minus 2 plus 2 n fractions. And the maximum fraction is this or this. So if n squared is greater than or equal to 120, all these fractions are okay. So in case 2, I should consider the case that n is not greater than or equal to 11. So n is less than or equal to 10 because n is k times k plus 1. The only case that satisfies this is when n is 6, because 2 times 3 is satisfy this, but 3 times 4 is 12. So you don't need to check 12. The only case that is left in case 2 is when n equals 6. For n equals 6, I said this example, 1 over 3 plus 1 over 4 plus these 6 fractions, and all of them are less than the denominators, less than or equal 36 is correct. 1 over 12 plus 1 over 24 is 2 plus 1 over 24. If you use common denominator, it would be 1 over 8, 1 over 8 plus 1 over 8, 1 over 4, 1 over 4 plus 1 over 4, 1 over 2, 1 over 3 here, 1 over 6 here. Sum of them equals 1, and we've proved for all cases.